Hello and welcome back to Complex Analysis. And you might already know, first I want to thank everyone who supports this channel on Steady via PayPal or by other means. As a supporter, you have access to quizzes and PDF versions of all the videos. Now, in today's part 17, we will start talking about the complex integration. This means we will define an integral for complex functions. So when you have a function f from c to c, an integral should make sense. In fact, we will see that the most useful definition will be a so-called curve integral. The meaning of this is that the function f is integrated along a given curve. For this reason, there are a lot of other names that describe the same thing. For example, you see line integral or contour integral. Of course, the idea is always the same. You start with a curve in the domain, often called gamma, and then you apply the function f to go to the codomain. So as often in complex analysis, we map the complex plane to the complex plane. Then, of course, on the right hand side in the codomain, the curve could look completely differently. Okay, now with these informations, we will be able to define the integral of f along the curve gamma. And then we write this as the integral f of z dz. And please note, the result here should be a complex number. Okay, now the precise definition of this object I will give you in the next video. Here in this video I want to start with a much simpler integral. In fact, this is needed to understand this complex curve integral. And I just call this a complex integration on real intervals. So you already see, this should be connected to the ordinary integral in the real numbers. Now, the picture from above looks much simpler because it means that we want to map a real interval from a to b into the complex plane. And moreover, we just consider continuous maps. And indeed, I also want to call this map lowercase gamma. Therefore, you should see this is actually the first step from the picture above. However, now I want to concentrate just on this picture here. Now, we should visualize this first point here as the starting point gamma of a. And then the last one here could be gamma of b. In other words, if this map gamma is nice enough, this interval is just transformed into such a curve. And then we don't have any problems defining the integral for gamma. Here please note, this is indeed something new because the map is complex valued. However, the integral symbol looks the same as always. This is because the domain is still in the real number line. And exactly for this reason, defining this integral is no problem at all. We can just construct it with two real integrals. Namely, we just take the real part of the function gamma, and then we add I times the imaginary part. In other words, we just look at the two components the function gamma has, and then we consider them separately in the integral. And in the end, we put them back together to get a complex number out. And here please note, these two integrals here are ordinary Riemann integrals as we have introduced them in real analysis. More concretely, they are well defined because we have continuous maps. Therefore, also this new complex integral is well defined for continuous functions. Moreover, we also find the usual calculation rules for this integral, such as linearity, which simply means we can pull out scalars and sums. However, on the other hand, you might remember that for the Riemann integral in R, we have something like monotonicity. Now, since the complex numbers don't carry an order like the real numbers, we can't have it for this integral. However, we are able to substitute it for an estimate with the absolute value. Indeed, this is an important property we will need throughout this course. It tells us that we can estimate the absolute value of the complex integral. Namely, it's less or equal than the ordinary real Riemann integral where we put in the real function given by the absolute value of gamma. Okay, now before we prove this important property, I would say let's first look at an example. Indeed, what will happen a lot is that we look at a circle in the complex plane. Now, this is not hard to describe. We just choose gamma with domain interval 0 to 2 pi, and gamma of t should be given by e to the power it. So simply the exponential function of it. Okay, now with the picture from before, we know this describes a circle in the plane. Moreover, it's the unit circle and the start and the end point lie here at 1. Indeed, when you start at 0 and then you increase t, you go around the circle in this way. Here please recall, we know this from the exponential function. Okay, then in the next step, let's calculate this integral here. In other words, we have the integral of the exponential function of it, and maybe let's do it for arbitrary a and b. Now, by definition, we know we first have to integrate the real part, which is the cosine of t. And then we have plus I, the integral of the imaginary part of exponential function of it, which is, as you should know, the sine of t. And then you see, we have two real integrals we can easily calculate. Simply because we have the fundamental theorem of calculus and the antiderivatives of the two functions. The first one is simply sine of t in the boundaries of b and a. And the second one is minus cosine of t with the same limits. And for this reason, we are able to simplify this and write it as one function. Namely, we could write minus I cosine in front plus sine of t. And then you should see it should be possible to factor out the minus 1 here. In other words, we can write 1 divided by I times cosine of t plus I sine of t. And now when you see this, you should recognize this is again our exponential function. In short, it's 1 over I times the exponential function of it. In the end, you see, this is of course the antiderivative of this function here. Or in other words, the fundamental theorem of calculus should also hold for this new integral here. Now, this is not hard to show, because it simply works with the real and the imaginary part here. Therefore, solving integrals by the fundamental theorem of calculus is not harder than before. Okay, then let's go back to our important property here, and now we want to prove it. Now, obviously, this statement here is correct when this integral here is 0. Therefore, we only need to consider the case that it is not 0. However, in this case, we can bring the integral to a real number. For this, please note, in general, this integral here is a complex number. And maybe for the moment, let's call it w. And now we are able to normalize this number, and we can define c as w divided by the absolute value of w. Then we are able to multiply c inverse with the integral and get a real number. Simply because this is then the absolute value of w, so on the real number line. Okay, then here on the left hand side we can manipulate the integral. For example, by linearity we can pull c inverse into the integral. However, now we know this integral here does not have an imaginary part. To put it in other words, by the definition of the complex integral, this is equal to the integral of the real part. Moreover, now about this real number inside the integral, we can say something. More precisely, we know that the absolute value of the real part is always less or equal than the absolute value of the complex number. This is simply a fact that holds for all complex numbers. Also, the absolute value is multiplicative. Hence, we can split it up, and then we have here the absolute value of c inverse. However, this complex number lies on the unit circle by definition. More concretely, the absolute value is equal to 1. Okay, and now here you should see we have an inequality for real functions. Hence, we can use the monotonicity of the ordinary Riemann integral. This means that the inequality still holds when we look at the corresponding integrals. And now when you recall the important property from above, the one we want to prove, then you see this is the right hand side. And now we only have to reformulate the left hand side to get this left hand side here. And exactly for this reason, we made this integral here real. Because now we can just use this fact here for a real integral. Of course, this is something we know already holds. So without a problem, we have the inequality here for the real part. And exactly here, the equality from above comes in. So this is exactly the absolute value of this integral here. And now because we have chosen c to be on the unit circle, it will vanish in the absolute value as before. In summary, you can see we have proven our important fact from above. Indeed, you see the proof was not so hard when you have this nice idea to make the integral real. However, it's not important to remember the proof, it's important that you remember this important formula here. Moreover, now you also know a lot of properties for this complex integral come immediately from the real counterpart. For example, as we have discussed it before, the fundamental theorem of calculus, but also the substitution rule or the integration by parts formula. Everything is not hard to show at all when you have these properties for the ordinary real Riemann integral. However, the next important part is to extend this to the complex curve integral. And of course, this is what we will do in the next video. Therefore, I really hope that I see you there. Have a nice day and bye!